In this video, I want to talk a little bit about implicit functions and then implicit differentiation. This is lesson 3 for part 3 of unit 2 in calculus. So when we write functions where a single variable is not identified, we call this the implicit form of a function. And so if we were to transition from implicit form to explicit form, which we're most comfortable with, one thing we might do with this particular example is to solve for y, and that's pretty traditional. So we could subtract 2x from both sides and then divide by -1, and we have 2x plus 3, and this is what we would call the explicit form. We've written this function explicitly in terms of x. So y is the result of some modification on x. These two essentially mean the same thing. It's just that this form on the right is a little bit easier to work with when we're trying to identify a value for a dependent variable. And we could do the same thing with this example here. We could subtract 2x and 10 from both sides of the equation, then divide both sides by -5. And this would be okay as a final answer. However, if we report it in slope-intercept form like we often do with these types of linear equations, we might see this. The -2 divided by -5 becomes a positive fraction, 2/5, and -10 divided by -5 is a positive 2. And so there we have our explicit form. For this logarithm expression, this is kind of interesting. One of our log laws says that if I've got the product inside of an argument, I can actually split this logarithm into 2. Then we would have log of y equals 5 minus log of x after we subtract log x from both sides. And then using our understanding of logarithms and the implied base of 10, I could rewrite this logarithm from the left as an exponential on the right. And we know that y is equal to 10 to the 5 minus log x power. So we've got y isolated, or we have solved for y explicitly, and that would be 10 to the 5 minus log x power. So in virtually every case, if we've got an expression or an equation, I should say, written in implicit form, we can solve for an explicit solution. Now when we start seeing examples like this one, things start to get interesting. Of course, we can subtract x squared from both sides. But now, when I take a square root in order to isolate this y component, we got to keep in mind that 2 solutions are produced. We have the positive square root of 1 minus x squared, and we also have the negative, or the opposite of 1 minus x squared. Since we had to put this radical symbol on paper, we had to be prepared for both solutions. And so as far as our explicit form goes, we have y equals the square root of 1 minus x squared, and we also have the equation y equals the opposite of the square root of 1 minus x squared. Now what I find kind of interesting about this is that if we graph both of these, we'll get an image that looks like this example that I've shown up here. In this green arc, we see the positive square root of 1 minus x squared, and in the red arc, we see the opposite. It's hard to read that, but that's the negative symbol, the opposite of 1 minus x squared. And of course, when you put them together, we get a circle. And if you recall your rules from geometry or any of your studies in conic sections, you would recognize that this pair of equations does produce 2 semicircles. When combined, we have a full circle. And that's all well and good, but the issue that I have with this example is that we needed 2 equations. We needed both of them in order to make a circle. So both equations needed to be graphed in order to make a circle. If we had left our function in implicit form, however, like we have here, if we had this equation graphed, and again, back to our discussion of conic sections back in Algebra 2, we would recognize that x squared plus y squared equals r squared. This is the generic form. Actually, there's a little bit more to it than that. X minus h squared plus y minus k squared equals r squared. That's our general form of a circle, where h and k represent the center and r represents the radius of the circle. So we can now generate the entire image of that circle with one equation only. One implicit equation would be sufficient. And so sometimes it's helpful just to deal with implicit functions to describe a particular image. Now, one thing we've got to be careful of, and I think I've already made the mistake here in this video, is I've called this an implicit function, and it's not a function. Remember, this image fails the vertical line test. This graph fails the vertical line test. So we can't say that this is a function. It must be identified as an equation or relationship. It is not a function. And if my handwriting's a little sloppy, let me clarify that. One implicit equation. There we go. That's a little bit easier to read. Now, if we were to work with an implicit equation, we may still need to analyze the behavior of this graph at different portions of that graph. And so I've got a question over here on the right-hand side. What is the slope of the tangent line when x equals 0? Well, here's a point where x equals 0, but here also is a point where x equals 0. So we have the coordinate at 0, 1, and also the coordinate at 0, -1. Now, we're pretty lucky here, at least I say we're lucky, because the slope of the tangent line at both of these positions is equal to 0. The slope of the tangent line is equal to 0 at both points. But you can imagine that we've got a bit of a problem if we look at other x values. And in this case, we're asking about when x is equal to radical 2 over 2. Now, I chose that point because it should be familiar to you. That's this position right about here. This is where x is equal to the square root of 2 over 2 and y is equal to the square root of 2 over 2. And you might be able to guess what the slope of that line is at this particular point. Now, we've also got another point down here that also has an x value of radical 2 over 2. So x is radical 2 over 2 and y is radical 2 over 2. Down here we've got an x that's a radical 2 over 2. But the y is the opposite of radical 2 over 2. These are coming from our unit circle definition from trigonometry. But back to the discussion of slope. What's the slope at this position and what's the slope at this position? So I'm going to label it this way, m tangent, and then we'll use this vertical bar at radical 2 over 2, comma, radical 2 over 2. So this notation is implying that we're looking for the slope of the tangent line at this particular point. And if your guess here is that the slope is -1, then you are correct. That slope is -1. But the slope of the tangent line at radical 2 over 2, comma, negative radical 2 over 2, well, the slope at that particular position is +1. And so you might be wondering, well, don't we have derivatives that help us find slopes? How could we use a derivative in this particular case? And, well, you're absolutely right in thinking that. We can establish a derivative function, and we could find the slope of any position on this particular graph. The interesting thing about these implicit equations, however, is that we need to provide both an x and a y coordinate in order to find the slope of these particular points. Because as you can see here, when the x values are the same, but the y values differ, it's entirely possible to have two different slopes. And so if we remind ourselves about this Leibniz notation, which we're going to use pretty exclusively for implicit differentiation, let's remember that we're essentially applying a derivative command. This d over dx is our instruction to find a derivative on both sides of the equation. We don't know what the derivative of y is with respect to x because those variables are different. So we're going to leave this differential notation as dy dx. But we have a rule for finding the derivative of a function or an equation that's written with the letter x, and that's what we call our power rule in this case. And before I jump to this solution, I think it would be good for me to point something out here. As an intermediate step, something that we've already done in the past and we're so comfortable with it now that we forget about, by applying this derivative command on the outside of a large group, that's as if we're applying that command to every component on the inside of that group. So d dx of everything. And our sum and difference rules allow us to find the derivatives very quickly. So the derivative of 1/3 x squared was 2/3 x to the first. Our derivative of 7x is 7, and the derivative of this constant is 0. And that's how we ended up with this solution. Utilizing this technique might be helpful when we apply implicit differentiation. So here we go. Here's the brand new stuff for our calculus class. Let's say we've got x squared plus y squared equals 1. And I'm being deliberate here with my spacing. I want to give myself some extra room. We can actually find the derivative of this function without isolating y. We don't need an explicit form of the equation in order to find this derivative. And we're going to use the derivative to find the slopes at these particular points, so two of which we should know the answer to, and then two other ones that are brand new. But we should be able to find the derivative using implicit differentiation. So if my job is to find the derivative, I think what we're going to stick with is the derivative with respect to x. We'll go ahead and apply that derivative command or set of instructions to each of these terms. Now here again, speaking of variables, we're asking to find the derivative in terms of x. So I have a rule that allows me to find this derivative. That's simply 2x. That's the power rule. Now this intermediate step, this is where it gets a little bit strange, and this is where the implicit differentiation comes into play. We again are asking for the derivative in terms of x, but we're supplied with a variable y. And when those two variables disagree, we technically don't have the differential in terms of x, but it's instead in terms of y. So what we would do to solve this is we would apply a mini chain rule. And I'm not going to discuss this in depth in this particular video, but if you're interested in understanding why it's the chain rule and why we have to use this particular process, I would recommend doing some additional searches for implicit differentiation online and read some websites or watch some other videos. You'll see other mathematicians talking about the workings behind implicit differentiation. But what we're doing is we're applying a chain rule here where y is our inner function, and we don't know the derivative of that inner function, but you'll see why that's going to be helpful for us in just a second. And then we've got y squared that's acting as an outer function. So if you recall with the chain rule, we would take the derivative of the outer function, which would be 2y, and then immediately multiply by the derivative of the inner function. We don't know the derivative of the inner function, and I'm using air quotes here, the inner function of y. So we're going to leave that inner function derivative as this differential, dy dx. So again, derivative of the outside function, keep the inside function, multiply by the derivative of the inner function. The three steps of our chain rule have been applied. On the right-hand side, we're asking for the derivative in terms of x, but we don't have an x variable here, and that's okay because this is just a constant. And the same rules that apply to our, or it's the same derivative rules that we've been using all along. The derivative of a constant will, of course, always equal 0. Now that we've got the derivatives implicitly described, let's see if we can isolate this dy dx, because that's the notation that's being used to represent our derivative. Let's go ahead and isolate that. So I'll subtract 2x from both sides, and we've got 2y dy dx equals negative 2x. Then I'll divide both sides by 2y, and now I've got dy dx, the differential of y with respect to x, equals negative 2x over 2y. And if we simplify dy dx, then of course is negative x over y. And this is strange, but that's the solution that we're after. This is the derivative defined implicitly from both x and y. And you can see here that this function does rely on an x and a y variable in order to compute the derivative. So let's see what happens. What if I use this differential, dy dx, and I evaluate it at the position radical 2 over 2, comma, radical 2 over 2. Now we think that this slope should be equal to negative 1. Let's see what we get. I need a negative x divided by the y coordinate, and the x coordinate was radical 2 over 2, the y coordinate was radical 2 over 2. And sure enough, when I have a number divided by itself, I get 1, and because of this negative sign here, I have a solution negative 1. So the derivative at this particular point, according to our equation, is negative 1. I could do the same for the other point, which we hope is equal to a positive 1. And you can probably already see what's going to happen. When I divide a negative x, or the opposite of x, by our y value, well, we get the division of two of the same fractions that equals 1, and the negative signs will cancel, and we've got a positive 1 solution. So our guess as to the tangent line slope up here was shown to be correct by using our derivative rules down here. So what about the other points? Now, these other equations should look familiar to you, or I'm sorry, the other coordinates should look familiar to you, because we have 1/2, comma, radical 3 over 2, and then 1/2, comma, negative radical 3 over 2. So these are additional points at the 60-degree marks that show up in our unit circle. So what's the slope at these positions going to be? Go ahead and pause the video now and try calculating them on your own. You can resume playback in a moment to check your work. And here again we supplied an x and a y coordinate, the opposite of x divided by y. In the first case here we have a slope of negative 1 over radical 3, which is approximately negative 0.5774. I'm okay with answers that haven't been rationalized, but if you come from a background where your math teachers have told you to always rationalize the denominator when there's a radical there, then go for it. The decimal values should be equivalent regardless of our solutions, whether they're rationalized or not. In the second example, we see much of the same thing, except the two negative signs do cancel each other out, and we're left with a positive slope of 0.577. And while the sketches of these derivatives may not have been perfect, hopefully there's a bit of an argument here that makes sense that the slope at this particular example is not quite as steep as this green one. And same thing over here, the slope at this orange line is not quite as steep as this green. So it's somewhere between 0 at the peak of the circle and 1 at the middle section of that circle, and 0.57, of course, is in between those two. So let's go ahead and try that for this new function down here. It's a little bit tight, but there's the function, x minus y squared. X minus y squared equals 3. And I may cheat again a little bit, give myself some extra room. X minus y squared equals 3. If I apply my derivative notation to all of these terms, we could then evaluate the derivative of each. Well, the derivative of x with respect to x, that's easy. Those two variables match, and the derivative is 1 here. The derivative of x is equal to 1. The derivative of y squared, now y is a different variable than x, so we're going to use that chain rule. Find the derivative of the outer function, 2y, multiply by the derivative of the inner function, which we don't know. That's the dy dx component. And the derivative of our constant here, of course, is 0. We can do the math to isolate dy dx by subtracting 1 and then dividing by negative 2y. And we see that dy dx is equal to 1 divided by 2y. And on the right side of our handout, we've got our function. I should say equation, it's not a function. We've got our equation that's represented by that particular graph. And here again, we can find the slope of any point along the way. Now, some of these points are a little bit more obvious to use than others. Sorry about that. Some of these points are a little bit easier to identify than others. 0, 0, 4, 1, 7, 2. Those are all points that fall nicely on these lattice marks on the graph. And again, with an x and y component, we can find the derivative using the implicit derivative. Now, what's particularly interesting about this function is that we don't need an x value. No x value needed. And instead, the derivative is dependent only on the value for y. So if you'd like to, you can compute the derivative of each of these functions. Your guess right here might be that this derivative is undefined, and you would find that that is true. The dy dx utilizing 1 over 2 times the y component, well, we end up with 1 divided by 0, which is undefined. The dy dx at 4, 1, and maybe I should have included this notation here. Oops, sorry, not 0, 0. What am I talking about? This is 3, 0. There we go. So that 3, 0 was undefined. At 4, 1, well, again, we don't need the x component. We just need the y component. This is a half. So that seems reasonable. We have a slope of a half right here. And then the slope dy dx evaluated at 7, 2 ends up being 1 divided by 2 times 2, which is a fourth. And the steepness of this line here is less than the steepness that we had back here. And according to my calculations, that steepness is 1/2. Now, in the opposite positions of each, you'll recognize that the slopes are now decreasing, and that's accounted for if we were to change our sign for the y value to be -1. Well, then our slope obviously becomes -1/2, and then -1/4 for the mirror copy down below. So let's try one more example, and I might have you do this one on your own. We've got a pretty wild-looking curve here. This black curve is described by this particular equation. It's a bit challenging for you to do on your own. I'll walk you through this one. And so we've got this particular curve, and we would like to know what's the steepness or what's the slope of this tangent line at the coordinate 3, 2. Well, the first thing we need to do is find the derivative in terms of x. So I'm going to space out this equation, x squared plus xy minus y cubed equals 7. And as I do that, I've got room to identify my differentials. And as we find the derivatives, let's go ahead and double check whether the variables match. So x and x, they match here, so I'll just use my regular derivative rules. For this one, we've got a product happening here, so we've got an x times a y. I know the derivative of x, but I don't know the derivative of y. That's the differential that we're after. So let's think of our product rule. The product rule says that we should find the derivative of the first function and multiply it by the second function untouched. And then to that we add the first function times the derivative of the second function. And again, we don't know the derivative of y with respect to x. That's exactly what we're solving for. And by using the product rule, we ended up with these two terms, the sum of these two terms. We'll use the chain rule as we have in the past for this last term, the derivative of the outer function, 3y squared. We keep the inside function alone. The y component is acting as our inside function. And then we turn around and multiply by the derivative of the inner function, dy dx. So our objective, of course, is to isolate dy dx. That's what we're looking for. That's the solution that we're after. And so from here on out, it just takes a little bit of algebra to make that happen. First thing that I'm going to do is just drop the grouping symbol here and then the unnecessary coefficients. And then I'll start to isolate the terms that contain dy dx. Because we're ultimately going to factor. We're going to treat these two as common factors amongst these two terms. So I'm going to move the 2x and this y to the other side of the equation. Simultaneously, well, no, I'll do this in a second step. So we've got x times dy dx minus 3y squared times dy dx, and that equals negative 2x minus y. Now, hopefully you notice that this dy dx is multiplying by x and also multiplying by 3y squared, so it's acting as a common factor. So I'm going to factor dy dx as a common factor out of the term x minus 3y squared. And by doing so, hopefully you see what we're going to do next. Our job is to get this dy dx all by itself. So if I divide both sides now by this expression, I have the dy dx differential identified. And now we've got the expression that can be used to find the slope at any given point. So this is the differential, and we need to find the slope at 3, 2. Now, if I'm not mistaken, this graph is drawn pretty much to scale, so it kind of looks like we have a slope of around 1, if I had to guess here. Let's see what happens when I do evaluate this differential at the coordinate 3, 2. So here I've made my substitutions, negative 2 times 3 minus 2, divided by 3 minus 3 times 2 squared. And in the numerator, we end up with negative 8. In the denominator, we get negative 9, which is going to simplify to 8/9. So again, I predicted that the slope was about 1 just by looking at the scales here, and that's 8/9 is awfully close to 1. But we're still not quite finished yet. This problem asked for the equation of the tangent line, not just the slope, but the actual equation of the line. So let's go ahead and figure out the rest. We've got the slope, we've got the point. Let's go ahead and generate the equation. So by using the point-slope formula, we've got y minus 2 equals 8/9 times the quantity of x minus 3. So after distributing, we've got 8/9 x minus 24/9. Now 24/9 is can be reduced, but I'll do that towards the end here if we need to. To add 2 to both sides, that would be adding to this 9th. I'm going to add 18/9 to both sides, just so that we have a common denominator. And that ends up being a negative 6/9, and when simplified, we have 8/9 x minus 2/3. And there's the answer that we're after. It took us 2 or 3 intermediate steps, but we finally got there. If I were to extend this line, it looks like it makes sense to me Does it make sense to you? It does appear that this intersection is at approximately negative 2/3. And one more time, we've got a slope or a rise and a run of positive 8/9. So there's a lot to discuss in this particular video, but this implicit differentiation is the key for this week. I would again recommend that you watch a couple other videos from other online mathematicians, or perhaps read some articles online about implicit differentiation. The help tools in Math Excel are also nice to reference. But start practicing more and more with these. In fact, the next series or the next video is just a series of implicit differentiation practice. So I'm going to go through several of those solutions in the next video. I hope this one helps. If you have any questions, please let me know. Thanks for watching.